this last series of videos in our study of heat and diffusion, we'll be talking about heat transfer. We'll be asking, how does heat move? And what determines the rate of heat flow for different systems? This is relevant when we try to consider too how we can stop heat flow, i.e. when we want to keep ourselves warm or our houses warm in winter or cool in summer. So let's start considering the three mechanisms of heat transfer, reminding ourselves that heat will always be transferred from the hotter to the cooler region until thermal equilibrium is reached. There are three mechanisms for heat transfer that we are going to study here. The first is conduction, then convection, and then radiation. These three mechanisms are illustrated here with a campfire. Conduction could be seen by poking an iron rod into the fire and feeling the heat transferred from the fire up the body of the metal rod to your hand. Convection, the warm air rising in the top of the campfire. And radiation, the radiated heat of the campfire, which can be felt in all directions. The first mechanism, conduction. Conduction is due to collisions or increased vibrations being transferred between the atoms or molecules, and this generally occurs most efficiently in a solid. When we're talking about heat flow, we're talking about heat per second. This is the rate of heat flow. To illustrate the rate of heat flow as a result of conduction, let's consider a metal rod of length L and area A. We'll have the bar hot at one end, so we'll have a temperature 1, and cooler at the other end, temperature 2, so we have a delta T across the length of the rod. Now let's consider what our heat flow will be proportional to. We could imagine if we have a greater area, we'll have a greater lot of heat flow. So we can have our area here, and if we had a larger delta T, if it was really hot at one end and really cold at another end, you would imagine heat would flow faster. So we can have our delta T here. Now to consider the length. If our rod was really, really long, you would imagine that it would take a long time for the heat to flow. Our rate of heat flow would be decreased, therefore our length has to go under here. Now, if we want to turn this into an equation, we need a proportionality constant, and it's another one of these proportionality constants that's specific to the materials. This time we have Kc, where Kc is the thermal conductivity of the material. This gives us our heat flow, Q on T, equals Kc A delta T on L, where A is our area, delta T is the change in temperature, and L equals the length. Here is a table of some thermal conductivities. I'll add one of my favourite materials, diamonds, to the top here, because diamond has got an extraordinary thermal conductivity. It has about 1,000 joules per second per metre per Kelvin, which is really, really high. This is in contrast to something like roof insulation, which has a very low thermal conductivity, and this is of course because we want to stop heat flow from occurring. Just a note about the units of thermal conductivity. You may notice we have joules per second at the beginning here, and you might remember that joules per second is the units of power, or watts. So sometimes the units of thermal conductivity are written as joules per second per metre per Kelvin, and sometimes they're written as watts per metre per Kelvin. Now let's use this equation and do a quick example on thermal conductivity. The question is, how much heat flows through a layer of body fat of a seal, this guy here? We'll assume a skin temperature of the seal sleeping on the ice of 0 degrees C and a core temperature of a seal of 38 degrees C, similar to us. The area of the seal is approximately 0.75 meters squared, and it has an average fat layer thickness of 5 centimeters. Our Kc for fat from the previous slide is 0.2 joules per second per meter per Kelvin. So now we can use our equation for heat flow via conductivity. Q over T equals Kc A delta T on L. And if we put those numbers in, we can see we get a value of 114 joules per second. So with delta T, it's okay to stay in degrees Celsius, as it is the temperature change that's required for this question. And remember, delta T in degrees Celsius is the same as delta T in Kelvin. Also remember to put all the units in SI units, so we've changed our 5 centimeters to meters. I'll get you to think about what would happen to the heat flow if the seal got really fat, had a very good season, and doubled the fat thickness.